Okay, so last time we introduced the LLA grammar. We said, why do we want the LLA grammar? If you remember, we said we want it because to solve the issue of what? Who remembers? Ambiguity. We said, okay, without the LLA grammar, if you just have an abstract grammar, you may fall in the trap of ambiguity. And by ambiguity, how can we detect it? Just if you want to remind me. Yeah. Exactly. If you can produce more than one parse tree, that means the grammar is ambiguous. Now, in the past, I used to ask you, how can you solve this? You said, okay, we're going to change the grammar, and then you have to think about it, how to change. Now, of course, there is a formal way to change the grammar with specific steps that it will always work. It's called LL grammar. But we said one of the problems with LL grammar is that because it's always from left to right, and then we're always expanding leftmost, we're going to fall into something called left recursion. We explained all of this, right? So we came with all of this. We gave an example why it will work, and then now we're going to learn the thing. Okay. And then I asked you here, can you help me find a solution why this is happening? And if you remember, some of you, we had mixed things. How can we change A? Because the problem is that we're always, what? Falling back into A. So if I do this, so we said why we're having the left recursion, if you remember, because if I have these grammar that, let's say, B equal non-terminal, which is, for example, 3 or whatever. But because A is going to always be left expansion, right? So I'm going to get stuck into a loop. Each time I call A, I'm going to call A again, okay? And we brainstormed together. Some of you said, like I said, let's get rid of A. But what did we say? Okay, if I get rid of A, I'll end up with a grammar like this, plus B. No. Others say, okay, let's replace A by B. Then we said, no, it's not going to work because I'll end up with changing the whole grammar. It will be plus B, like this is different grammar. So I want to find a way to keep the same grammar, but don't let it get stuck with the non-terminal. Each non-terminal is acting like a subfunction, right? Like a function. So in this case, what's going to happen, because we saw the solution, we're going to just add new non-terminals. So let's see how can we do that. So why is this happening? We said direct left recursion, and then that's how it's going to be. So for every direct recursive rule, it has this shape. So that's the shape now, before changing it. We'll always have a non-terminal, and then after it, we'll call this alpha 1, and then we'll have the B here. So how can I change it? I'm going to introduce. So what is beta here? Beta is something that does not begin with a non-terminal. So my aim here is to follow a step where I don't get stuck. So I want to add something that doesn't begin with a non-terminal. How can I do that? So we want to introduce a new non-terminal A prime and replace the rule by this rule. So now, if I take this, I will say my new rule is beta, which is anything that is a non-terminal. And then I'll call A prime. Okay? Now, what is A prime? A prime can be anything like alpha and then A, or empty. Why? Why is empty is very important? Do you remember? Because I showed it to you in the tree. Why is empty is very important? Benjamin.
It's a stop.
Yeah, but why? Why? Because in the original grammar, we don't have empty, but why do we want empty? Yes? Not just that, it's because we're introducing many new non-terminals. Okay, I need to get rid of these non-terminals at some point. So I need to be able to replace them with empty, because if I just introduce non-terminals, I'm stuck with many non-terminals. So the idea here, okay, I'm going to add a non-terminal, but I will allow this non-terminal to also be like empty, so I can get rid of it. So this procedure will not eliminate indirect recursion. We don't care about indirect left recursion. Now let's focus on just the direct left recursion. What do you mean by direct left recursion? Is this, like it's directly very obvious that we have a left recursion. It's called direct left recursion. That means I'm going to get stuck here. Indirect is that, for example, I have B plus C and B is then A and then, so it's indirect way. It's more complicated. We're not going to focus on it. Yes, Anju.
So why do we need A if we have A?
Because A prime, I just created it. Because the original grammar is A, right? So the way here, the way you want to think about it is that I have a grammar. I need this grammar, it's arithmetic grammar. So I need this grammar, but I need to find a way to not get stuck and a left recursion. So I cannot just change the grammar. I need to just change the structure of the grammar while keeping the foundation of this grammar. And for example, if I'm writing grammar about if statement, about if and else, I cannot say, okay, because I'm getting stuck in the left recursion, I'm going to change it to be, there's no if, to be a for loop. I can't. I changed the whole grammar. I need to change it in a way where it will keep the solid structure of it. So by introducing A prime, is just I'm just saying that, okay, I will do more terminals, non-terminals to be able to solve it. So now direct or indirect left recursion problematic for all top-down parsers. So this is also something important for you to know, that left recursion is an issue with top-down parsers. Bottom-up parser will not have this issue. They will have different issues, but they will not have this left recursion. Why? Who can tell me why we're not going to have the left recursion issue with the bottom-up parser? So what is it top-down? It's from top till down, and it's what? It's left to right, and also it expands on the left. What about the bottom-up? What did we say about it, Mateen?
So it's small, equals B to A, so it's small.
Not just that, but we said after we built the parse tree, how is the parser reading it? From right to left. Do you remember? There's a very there's a slide here. If you go back, we gave an example, and we said the bottom up expands on the right. So if the idea of a bottom up that expands on the right, I'm not going to get stuck in a left recursion because I'm expanding on the right anyway. But it will have its other issues. Now you may ask me, why can't we just use bottom up all the time and I don't have to, correct the grammar and do all of these extra steps? The reason why top-down parser is much easier to be written by hand. We're going to see that bottom-up is more complicated, so you need to have something called parser generator. So you need to get a program that will generate the parser for you. The parse tree is more complicated to be written. So that's why it's better maybe sometimes to fix the issues in the top-down and use top-down. But also bottom-up is used also. So now, yes.
Picture in the previous slide. This is just in a general case for
This is the general grammar. This is the general idea. You don't have to follow the exact thing. For example, we'll take this example. Now it will make more sense for us. What did we say? Expression, I'm going to transform it to, instead of having all of this, I'll just, if you follow this, it will be the same as this one, but it just has so many more non-terminal. So what we did here, again, this is beta or alpha, right? And this is the A prime. So what did we say here? The A prime will have beta in it, okay? So let's say this is beta. Now, this M expression is here. It will also have what? Prime of this one with another beta. What is the idea of beta? That I need to reach a point where it's terminal. So let's follow it. So that's another beta and prime. Let's go to this beta. What is this beta now? It has a non-terminal. You see what I did? Instead of having them all on one line, it's confusing for the parser, it's ambiguous. I just added a non-terminal and connected with a non-terminal till I reached here. I helped the parser go there. So how do you want to think about this? If I tell you, Isad, if I want you to go to the site building, and I tell you, you know what? Just go to the site building. That's it. I just tell you this. Is this clear or ambiguous a bit for you? Because you don't know the site. You're going from here. How many roads do we have? Many roads. If I tell you, I want you to go to the site building. First, I want you to go. I don't even mention the site building. I'll tell you first, I want you to go to the student square. Then from there, I want you to go to the Tim Horton on the crossroad. Then from there, I want you to go to the pharmacy. Then from there, I want to go to the site. What did we do here? We actually just divided this site thing. We added just more stops for it. Did we change the original grammar? No. I just added more stops, right? Like more stops for the parser to do it step by step. It's just easier for him, more clear. Yes, Benjamin.
This make it less efficient though. Like if I say, okay, you're going to site, but first go to the Parliament building and then to site.
This is more efficient, but the way that I gave my example is still efficient because you're not going to the Parliament, then going to the site. You're actually just going to the site. It's in the same way, but you're having more stops. It's like the map. When you look at the map, they don't tell you just a point there. They will give you a road, like a road to go. But they will tell you.
How do we know that we have the fastest road? Because sometimes the map will give you 2 roads.
Because you're creating this. That's how you know. You're choosing it. Yeah. Yeah. No, you're designing this. That's what I mean. So when you're transforming this into an LL grammar, you're the one who's designing it. So you're going to design it in the shortest way that works. Is this the idea clear here? It's as simple as that. Okay, guys? Of course, in the tutorial, we'll try to do a few examples on how to solve it ourselves. But here in the lecture, I just want you to understand the logic, like the concept of this. Good? Clear enough? Okay. Now, what is the other problem for the LL that I need to solve it? There's something called disjointness. What do we mean by disjointness, guys? Is the inability to determine the correct right-hand side on the basis of one token. Why I care about this one token thing? I want you to think about it a bit. I'm saying that I need to solve this problem that if I receive a token, I need to be able to make a good decision. Why? Why can't I just, receive 3 or 4 tokens and then decide? What is the lexical analyzer doing? What is the role of the lexical analyzer? So this is the syntax analyzer. This is the parser. From where does it get the tokens? From the lexical analyzer. What is the role of the lexical analyzer? It's going to send me token by token. So it's going to give me 1 token. So I need to be able to use this one token to know where should I go. Okay, let's have an example that will make it clear. That means how to make a choice among alternatives. Let's take this as a potential issue. If I'm the lexical analyzer, and I'm sending you number 2. Michael, try to decide. You're the parser. Where should it go? Which road should it go? First, explain, think about it out loud. So I'm A. So do I have 1 option or 2 options? 2 options, this and this. I'm 2. Okay, where should I go? If you're think about it, just randomly. 2 is a number, right? So where should you go? Okay, you decided to go here. Who is a different parser and wants to have a different opinion on that? Isan.
First one.
Why? Because there's 2 also here. You're going to end up with number. So how is the parser able to decide? Because this will end by number, this will end by number for him. So it's going to be by luck if we don't give him something very specific. That's the disjointness issue. So that's why it's better to solve this by making it so clear for him that he doesn't have to take the decision based on his opinion, because we're going to end up with what? With a different answer. So look, if I use this road, I'll end up with just 2. But here I'll have 2 times A. So it's different. So it's not going to work. So we have to find a solution for this one. Yes. You can't. Why? Because if your prices are based on what? You see, no. We need, the goal of the parser is to convert or to get what the compiler designer wants. It's not everything. So like, let's say you wrote the grammar and you send it to me. If I'm going to just make prioritize on just out of my mind, I didn't actually convert what you want. And so you, as the designer of this code, you should explain for me very clearly what do you want. When you're sending me 2, do you want me to say, okay, equal 2, or do you want me to say 2 times something? What do you want? So the problem is with you, the designer, not me as the parser. Why should I make the decision? So that's why the designer need to be to solve this problem. How can we do that? So of course, let's understand the problem. I think we all understand it by now. We gave the example of 2 here. We're giving the example of 5, and then we're going to end up with 2 different things. It's going to be unambiguously. Now we can solve this by having more than 1 token, which we don't want this because we want to keep the lexical analyzer send me 1 token part, because you can say, okay, I have 2, send me the next token. If it's times, I'll go here, for example. But no, I don't want this. I want to have the power with 1 token to decide. It's more efficient. So how can we solve this? By looking at the input, we want to anticipate the choice. We said, okay, this is the formal way to look at it. And then here we're still explaining the problem. So we're going to have either the first root will be B plus A, right? So this is the first root, or you're going to have the second root like this right away to go to the number. And the problem is that what? They overlap, okay? So how can we solve this as a solution? Something called left factoring, because the grammar can be read like this. Of course, so this is the problem. The grammar can be read technically like this. So I have a num here and num here, so I'm going to have a problem. So what is the solution? Using left factoring. How can we do that? Again, introducing non-terminals. So I'll say A equal num. What is the something common? Is num. I'll say, okay, give me num. And then I have another non-terminal. Now this non-terminal can be what? Who can tell me? Mateen.
A or empty.
Very good. It's going to be plus A or empty. Or sorry, times A plus A, so like this whole thing, or empty. In this case, if I'm only sending 5, that's it. I want you to print 5. You're going to have 5 here, and then you go here, okay, empty. When you receive the next token is empty, so you're going to choose this, you solved it. But I sent you the first token, it's 5. Then what is the next token? It's times multiplication. Okay, so I'm going to choose this. The parser is not confused at all now. Okay, so in each case, it's going to be solved. Is this clear, the example? If it's not clear, I can re-explain. Yes, Michael.
But the lexical analyzer, let's say, for example, gives 5. Look at the grammar. We convert A to num with A prime. Then the lexical analyzer will send this one.
Yes.
See if it's either empty or the times.
Yes. So if me, as the lexical analyzer, my statement is, let's say I just have this statement, 5. I want you to print 5, for example. What's going to happen? I'm going to have 5A prime and then empty. But if my statement is 5 times, let's say 4, I'm going to send 5 first. So I'm here, 5, and then I'm going here now. The next token is times. So I'm not going to choose the empty. I'm going to choose times. And I'll continue doing this. Okay, good. Okay, so now for A, there is no choice. A is always like this. And then for A prime, we have a choice, but do they overlap? There's no overlap in that choice. It's either this or just empty. So there's no overlapping, so it worked. Okay, so this is the official way to define it. Now, this is from the book about the left factoring. What do we mean by it? And then here's an example of well-known grammar that needs left factoring. Who can help me solve this? What's the problem here, guys? I have S, a statement. This statement can be what? If E, then another statement. Or if E, then statement, else statement. Or just A, like a non-terminal, like whatever, like 2. And then E, this is the condition is B. So if B, like B is the condition. So who wants to play the role of the parser? And tell me why this is ambiguous. Just give me an example. Samuel.
For example, if we have if E then S else S, that's hard to say. And the first S is also an if E then S else, then we have an else that can be.
Yeah, but let's take it step by step. So technically, as the lexical analyzer will send you the first token. What is the first token? If. So if it sends to you if, you have to take a decision now. It's either you're going to enter this or you're going to enter this, correct? So are you able to take a decision based on anything solid? No, because I'm sending you only one token, if. So how can I know if this or this? I don't know. So that's why I need to change it in a way that it will make sense. Who can try to change it? It doesn't have to work. You said.
You would have like the entire if E then S, like have the
This and this, yeah.
And then you would have a separate rule for if E then S else S.
So I'll put here, for example, S prime.
Yeah.
Okay, and then S prime will be what?
S prime would be
Who wants to continue it? Michael.
S or empty.
Else S or empty. Who agrees with this? Who has different way? Mateen.
Couldn't you just, instead of saying if for the second one, just say elif? Like
Here?
yeah, like that.
That's changing the grammar again. So let's say someone wrote this grammar. I just want to make sure it's good. But like someone else will just change the grammar, yes. But in this case, anyone has different opinion other than like Michael? So let's see it. Exactly. So we'll have this. And then the S prime will be this. Now, why did we choose if E then S, not just if? We said like if S prime, blah, blah, blah. Guys, I want you to think a bit. Why did we choose if E then S, S prime, not like we did this, like if, because we were looking at one token, for example. So if S prime, and then here we have S prime is E, then S prime prime, for example. Annika, you had your race? Yes. Very good. So now we go back to Benjamin's example. Do I want to go to the parliament before going to the site? There's no need. If I know that this is the common thing between the two, why do I need to have much more steps? This is a common thing. There's no need for me to say if and then E, because I know this is a common thing. So if these are the common stuff, I'll just put them as a common step and then the S prime. Good? So very good. Now, why it's called LL grammar? Because scans from left to right and also generate expands leftmost derivation. Bottom-up parsing, we're just going to explain it very quickly for you to understand what it is. We're not going to cover it in this course. Again, usually there's a compiler course for everything, but here we're just understanding the concepts of the programming language. So we have something called shift-reduce parsing. It has several different forms. One of the forms is called operator precedence parsing, and another one called LR parsing. So this is a bit more maybe popular. So usually in the book, for example, if you have the book, if you're interested, you can take a look. Usually they talk more about the LR parsing. Inside the LR parsing, we'll have what? We have simple LR, SLR, we have CLR, we have LALR. So this is to reply to your question when we explaining the grammar slide, and I gave you this example just from the left to the right, just quickly, and someone asked me, is it always like this? No, there's many different ways, but the simple one that we used as an example is just an example for you to understand what's the difference between bottom up and top down. Now, what is the idea, or what is the advantage of parsing is that it recognizes any language for which a context-free grammar can be written. Also, is the most general non-backtracking. I'm not going to complicate you with all of these details, but technically there's something called backtracking and non-backtracking. The one that we explained for the top-down parser are also a non-backtracking. The class of languages that can be parsed by an LR parses the proper subset, okay, and then this is also important, is actually detect a synthetic error as early as possible during a left to right thing. So the only thing that I want you to maybe grab from this is that the main difference between bottom up and top down, bottom up will, after the tree, when you want to read, you're going to expand from the left to right. Sorry, you're going to read it from left to right, but you're going to expand from right to left. Okay, so that's the only thing that you want to know. Now, what is the downside? And it's easily prevented. As we said, the downside is it's harder to be made by hand. So usually, there is specialized parser automatically. For example, parser generator, very famous one is called YAC, yet another compiler. This is the one that usually is very famous to use to actually generate this, because it is a bit, as I said, hard to do it by hand. LR represents what? Again, as I said, left to right scanning. So we scan from left to right all the time, but how do we expand from right most derivation in reverse? And the K number is how many token I can use. So you'll have LR0, LR1, all of these things. And then LR parsers are table driven. So what do you mean by table driven? So we will have a table that has something called action and another thing called goto. Inside the action section, we'll have the terminals. Inside the goto, we'll have the non-terminals. So it will look like this. That's the idea of the LR parser. You'll have a parse stack, and then you'll have the input. Inside this parsing table, you'll have this. So the actions here, the terminals, the goto are the non-terminal. Why? Because you take an action with the non-terminal, with the terminal. It's clear for you, you take the action, but if it's a non-terminal, you want to go there to expand it, right? Like to continue expanding. So this is just an overview. We're not going to ask you too many questions about bottom up in this course.